All right. Next, we've got Jonathan Fajen from Stanford University. He is in computational chemistry under the advisement of Todd Martinez, and his practicum is at Los Alamos National Laboratory. Thanks, Jonathan.
Thank you. So today I'm going to talk about two stories trying to make correlated wave function methods more efficient in quantum chemistry, in particular using GPU acceleration and exploiting rank-sparsity electronic wave function. So as a quantum chemist, what I'm ultimately interested in is the design of molecules and materials for applications such as catalysis or photochemistry, where we might want to harness light energy to drive otherwise unfavorable reactions, or develop photostabilizers that protect against radiation damage similar to our genetic material. And in all of these applications, or other ones we might be interested in, what we want to do is use atomistic insight to extract design principles. And as an example of what that might look like and why this is difficult, we can think about if we simply want to arbitrate between the performance of two catalysts, or two candidate catalysts. If we look at this very simple potential energy curve for a transformation, take us from our reactants A to product B, to evaluate the facility with which these transformations can be affected, we might look at the activation energy or energy barrier associated with these transformations. And if we want to take these energy barriers and compute an experimental observable such as the rate at which this reaction proceeds, then we know from transition state theory that this rate is going to be proportional to an exponential of this energy difference. And this exponential here is really what makes quantum chemistry so annoying in some sense, because this is really punishing, right? So any error that we make in calculating these energy differences is going to be exponentially amplified when we go to try to compare with experiment. And so we need to calculate these energy differences to a very high degree of accuracy in order to be able to obtain reliable predictions. So how do we calculate these energy differences? Well, we start with our Born-Oppenheimer electronic Hamiltonian, which has in black a 1 electron component, and in red the 2 electron part. And this is just the Coulomb repulsion of all the electrons in our system and gives rise to all of the complexity really in solving this eigenvalue problem. But we can write down our time-independent electronic Schrodinger equation, H psi equals E psi, and we're going to solve an eigenvalue problem, so we need a basis. And we can start with our single particle basis functions, or molecular orbitals. And these are just taken to be linear combinations of atomic orbitals, which you might remember from general chemistry. So things like 1s or 2p, 3d functions, and so on. From these single particle basis functions, or molecular orbitals, we're going to construct many-body basis functions. So these are anti-symmetrized products of these molecular orbitals. We also call them Slater determinants. And these are just some filling of the m orbitals with n electrons. And so we can have our Aufbau configuration, which is just filling up the lowest n energetic orbitals with our n electrons. Or we can have excited configurations, like this here, we have a singly excited configuration, and so on. And in this basis of Slater determinants, we can express the exact solution to our electronic wave function, which will simply be a linear combination over all possible configurations in this Hilbert space. And so our exact wave function has some component of the Aufbau determinant, some of all the singly excited configurations, some of all the doubly, all the triply excited, all the quadruply excited, and this includes up to arbitrarily highly excited determinants. So obtaining the exact solution to the electronic Schrodinger equation in this Hilbert space is going to scale exponentially with system size. And so this is not feasible to do in practice, and we need to make approximations. And the specific flavor of approximation that we're going to talk about today is coupled cluster theory. So in coupled cluster theory, we make an exponential ansatz for the wave function. So our coupled cluster wave function is just given by the exponential of this cluster operator t acting on a reference determinant. T is a linear combination of excitation operators itself. So we have a sum over all of the single excitations characterized by a weight or amplitude TIA. So this tells me how important is this particular single excitation in my final coupled cluster wave function. And we can then go to double excitation. So now I have a bunch of double excitations characterized by their amplitude Ti, J, B, and so on. And to make this an approximation, to get a working set of equations, we need to truncate this expansion. And the most common level of truncation is after single and double excitations, giving rise to coupled cluster with singles and doubles, or CCSD. So here we have our CCSD cluster operator, and our CCSD wave function is characterized by these two operators, which amounts to a matrix of single excitation amplitudes and a fourth order tensor of double excitation amplitudes. From this wave function, we can project our coupled cluster Schrodinger equation onto the reference determinant to give us an equation for the energy, and onto the manifold of singly and doubly excited determinants, which gives us a set of coupled nonlinear equations for the determination of the amplitudes. The iterative solution of this set of equations has a compute cost that scales like n to the 6 with system size, and a memory cost that scales like n to the 4. So this is the storage of that doubles amplitude tensor. If we're interested in photochemistry, which we will be at the end of this talk, we also need to target electronic excited states. We can do this through the equation of motion coupled cluster framework, where we essentially diagonalize this similarity transformed Hamiltonian with a cost that scales the same as the underlying coupled cluster method. Okay, so if we go back to what we want to calculate, which is energy barriers for the prediction of rates, and we ask how well does CCSD do? Well, as we said, we need to be very accurate to get these, to make quantitative rate predictions. In fact, we need so-called chemical accuracy, or within 1 kilocalorie per mole. If we look at how a bunch of methods do across a variety of barrier heights, we see that CCSD here in the middle actually doesn't achieve the level of accuracy that we want. So we're not able to get routine predictions of energy barriers to our desired accuracy. And this is because neglecting triple excitations in the exact wave function is a significant approximation. It turns out that these triple excitations are really important to getting the correct physics. And we can include triple excitations by going to CCSD-T. That's this little bar down here on the right. You see that this does achieve the accuracy that we want. The problem is that CCSD-T is an iterative method which scales like n to the 8 with system size. And quantum chemists are often very patient. They'll put up with bad scaling, but this is too much even for us. So we're fortunate that it turns out that we actually don't need to account for the full triples excitations. We can actually treat a subset of the triples as a small perturbation on the CCSD wave function. This method is, well, there are many such perturbative methods. The most popular is called CCSD parentheses T. And it, as you see here, does achieve the requisite accuracy we want while being a non-iterative n to the 7 scaling method. So this, now we're in business. Okay, n to the 7 we can work with, right? Okay, so quantum chemists love this method. It's better accuracy cost trade-off has led it to be called the gold standard of quantum chemistry. But it turns out n to the 7 is still really expensive. And so the routine application of CCSD parentheses T to anything larger than very small systems has been limited to HPC applications and things like that. So what we wanted to do was develop a GPU-accelerated implementation of CCSD parentheses T, which would make the generation of high-level energy barriers and interaction energies, et cetera, more routine. And I want to highlight really two things that we focused on in this implementation, the first being the minimization of per GPU memory requirements, and the second being the maximization of GPU resource saturation where possible. And these are really two fundamental aspects of GPU programming, and I'll just touch on how they influence the design choices we made in this implementation. So the first one is memory. So if we look at the form of the correction to the CCSD energy that parentheses T gives us, we need to construct and then contract a bunch of 6th-order tensors. So that's not great. But if we look at the structure of this equation, it's actually fairly amenable to parallelization, because nowhere do I need to store or operate on the full tensor itself. I can slice this up and evaluate the contributions from various subtensors. And so the strategy that we employ is basically viewing this W tensor, for instance, as a stack of cubes. So the index running along the stack is ijk, and within the cube, we have A by B by C. And we want to tile over A, B, and C. So these are the virtual indices, or the unoccupied orbitals in our reference. And the reason we want to do this is that the virtual subspace is going to scale much worse with system size than the occupied subspace. So what we do is we take slices of each of these cubes corresponding to our tiles over A, B, and C, line them up in these subtensors, and ship each of these subtensors off to its own GPU. On that GPU, we evaluate the contribution to the triples energy for that subtensor and then accumulate them at the end. So it's a very simple parallelization strategy. In the worst case, we can shrink the size of our virtual indices down to 1, in which case we obtain a maximum memory requirement per GPU of occupied cube, which is actually better than our underlying CCSD implementation. But in practice, we size these to be as large as possible and still fit on the GPU. Now, when we go to think about latency or maximizing saturation, we can go through this simplified version of the algorithm, where we start by setting up our tile sizes. We copy over some piece of the 2-electron integral tensor from the CPU to the GPU, and then this is the meat of the algorithm here. We need to evaluate a bunch of permutations of W. And in each of these permutation loops, we need to copy over a piece of the doubles amplitude tensor. And then we need to form this contraction of the 2-electron integral tensors. And in step 6, then we need to contract these two together. So what we notice is that we can actually perform this copy of the needed doubles piece at the same time as we do this contraction of these two integral arrays to have both ingredients we need for step 6 on hand right as we need them. And we do this with this CUDA memcopy async function, which is really, I think, kind of cool. So we're able to couple these two steps and really push down the latency during this meat of the algorithm. Then we just need to do another of these 2-electron integral contractions and then compute the contributions to the triples energy of this particular submatrix, which we do using a custom CUDA kernel. And so this really allows us to push down the latency during the meat of the algorithm, and we're able to see this in the performance that we get looking at strong scaling across multiple GPUs. So we attain really good scaling across going up to 1 to 8 GPUs, even for fairly small system sizes where it's difficult to saturate the GPU. We also look at the composition of the total calculation time as we push larger and larger systems, and we see that we were able to push out to fairly large systems, so 35 water molecules here, before the parentheses T time in blue dominates over the rest of the calculation. So we're getting pretty good scaling across GPUs and across system size. We're also able to compare to other HPC implementations of CCSD parentheses T, and these are on a variety of system sizes, but all pretty large CCSD parentheses T calculations. And what we notice in this column is if we look at the total time that the parentheses T calculation is taking for our method in TerraChem and every other implementation, for these top 3, we're all faster. The only one we're slower on is this calculation down here with 1,000 basis functions, which is one of the largest canonical parentheses T calculations that has been done. And you see in WChem, finishes this calculation in about a little over an hour. We take almost 8 hours. But what's important to recognize here is that this WChem calculation was performed on 20,000 nodes on a supercomputer. We did this on a single DGX workstation. So pound for pound, we're really competitive with massively parallel implementations of this algorithm. As one kind of test or example showing what we can do with this new implementation, we calculated parentheses T level nucleobase tetramer stacking energies for every possible combination of our 4 nucleobases. And we're able to attain high level accuracy for certain contributions to these interaction energies, which were previously certainly non-routine to calculate. And so each of these calculations underlying this data set is one of the largest canonical CCSD parentheses T calculations that have been performed, and we can do them fairly routinely on a single node. So this is really exciting, and this is really where I want to leave off the story about GPU acceleration and kind of pivot quickly here at the end to some work trying to leverage Rank-Sparsity to gain computational benefits in couple cluster methods. So CCSD or CC2, which is an approximation of CCSD, is ultimately bottlenecked by the storage of this 4th order doubles amplitude tensor. And so what we thought about and what many people try to do is to exploit any low rank structure which may exist in this tensor. And so in particular, what we're going to do here is assert a factorization of this doubles amplitude tensor where I'm going to project into some low-rank subspace spanned by n-aux basis functions. And in that subspace, my doubles amplitude is going to be, rather than a tensor, a matrix, so capital TPQ. I can control the size of this low-rank subspace with some threshold epsilon, and then I'm just going to project my working equations into this low-rank subspace. And so by doing this, I hope to gain significant performance benefits by reducing the size of the working equations and reducing the memory requirements for the algorithm. And so we did this in the context of CC2, so rank-reduced CC2, and mainly interested in photochemistry here. So we're looking at excitation energies. And here I'm showing the accuracy of rank-reduced CC2 relative to its parent method. And these are all essentially negligible errors here, while we're compressing the doubles to less than 1% of its original size for this set of organic dyes. This leads to significant computational benefits as we look at the scaling we get moving from longer and longer linear alkene chains here. We see that even at fairly small system sizes, so 300 to 400 basis functions, our rank-reduced implementations are two times or more faster here. And we can push this to larger calculation sizes than are possible with our canonical CC2 implementation. So we can get out to systems with more than 2,400 basis functions, which is just not accessible with our canonical implementation. And so I'll kind of wrap up here by saying we've been able to leverage hardware acceleration to make more routine calculations of high-level wave efficient methods, and we Another direction is exploiting rank sparsity of the wave function to obtain significant computational savings with very little loss in accuracy. Moving forward, I think we'd like to explore more aggressive factorization techniques to lower formal scaling in these methods, and then thinking about applying these same techniques to computing forces or couplings to enable applications in molecular dynamics. And so with that, I'd like to thank many collaborators, including my advisor at Stanford and people that I worked with during my practicum, and of course, everyone at Krell for facilitating the last 4 years of my research. So thank you very much.